Okay. So I'm going to put one slide of history in because I love it. Galen, once again, in the 2nd century, believed that the right chamber of the heart received blood from the liver. Oops, where is it? Here. The natural spirits arose from the liver and went into the right chamber of the heart. In fact, what he was identifying was the inferior vena cava. Then he believed that blood seeped from the right side of the heart to the left through these nearly invisible pores that separated the two chambers. Of course, this is not how the heart works at all. This idea persisted all the way up to Leonardo, who also believed that the blood emanated from the liver going into the heart and then proceeding from one side to the other. What Galen was probably mistaking here was the occurrence of what's called a PFO, a patent foramen ovale. There is, in fetal circulation, there is a short circuit from the right atria to the left atria, so that I don't want to make this a long discussion of fetal circulation, but blood from the placenta, oxygenated blood from the placenta, enters the liver first and then goes to the heart by way of vena cava. So a vessel normally carrying deoxygenated blood is carrying oxygenated blood and then gets shunted over to the other side of the heart so that it can be distributed throughout the circulation. And this may be what Galen was confusing for the function or the exact mechanism of the heart. But of course, that's not how it happens. We're going to spend the day here talking about how the heart actually properly circulates blood to get oxygenated and then distributes that throughout the rest of the body. So today, first we're going to talk about the actual circulatory flow pattern of the blood in the body. And then we're going to talk just a slide or two about the microanatomy of cardiac muscle cells. And then we're going to spend the bulk of the lecture talking about the cardiac cycle, specifically the conduction system, what the ECG means. And from there, we're going to move into cardiodynamics. At the end of the lecture, if I have time, I will cover the autonomic innervation of the heart. If I don't get to that, I don't get to it. But I will chuck that into the next lecture. On Friday, I was trying to decide whether I wanted to spend the whole lecture talking about pathology of the heart. Really, this class should be 2 semesters. Whether I wanted to talk about the pathology of the heart, or would you let Jacob in? Or the regulation of blood pressure, which itself should probably take 2 lectures. So I've decided to try to do a little bit of both, but I'm going to prioritize blood pressure, and the autonomic innervation will lead into the control of blood pressure. So if I don't finish it today, I'll get to it on Friday. Quiz on Monday. For those of you who haven't picked up on the pattern, once I finish covering a topic the following class period, there's a quiz. So this cardio unit here will have a quiz on Monday, hopefully. Okay. So, all right. Overview of the cardiovascular system. So really, we have 2 separate pumps in one with the heart. We have 2 separate pumps in one. There is the right side of the heart, whose job it is to pump to first of all receive blood from the periphery of the body and receive deoxygenated blood, and then pump that blood out via the pulmonary arteries to the lungs, where that blood will get oxygenated, and then it will return to the left side, the considerably more muscular left side of the heart, whereby that now oxygenated blood is going to be ejected through the aorta to the rest of the body. And we see here a little bit more larger schematic. We have deoxygenated blood returning from the lower extremity via the inferior vena cava, upper extremity, that is the head and arms, via the superior vena cava coming into this right atrium, and then passing from the right atrium into the right ventricle through this tricuspid valve. It will get ejected through the pulmonary valve to the two lungs, at which sites there's going to be the oxygenation, return to the left atrium via the pulmonary veins. They're painted red in this picture because they're carrying oxygenated blood, but they are veins because they're returning to the heart. They're returning to the heart. And then the left ventricle, the muscly left ventricle, is pumping out through the aorta to the upper extremity via the brachiocephalic trunk, the common carotid, the subclavian arteries to the head and arms out here, and then the descending aorta arborizes down in the abdomen to the numerous branches for the lower extremity. Okay, so looking a little bit more closely at the heart, we see, first of all, this sac that is surrounding the heart, this pericardium. There is this is the serous membrane that we talked about in the very beginning of the year or the semester, where there is an epithelium and some underlying connective tissue, the parietal layer, and then there's a visceral layer laying right on top of the heart itself, and this is the pericardial cavity in between. This visceral pericardium is the word we use when referring to the entire serous membrane that is surrounding the heart. However, when we're talking about the heart itself and not thinking about the serous membrane, it can also be called the epicardium. The epicardium is that layer of visceral pericardium that's laying on top of the heart. And so beneath the connective tissue of this serous membrane is the bulk of the heart tissue. It's the myocardium. It's made of all the little cardiac myocardiocytes, the cardiac muscle tissue. And then on the inside is this endocardium. We have a layer of areolar tissue and endothelium that lines the interior of the heart. The heart muscle fibers themselves are not just laid down in a flat pattern. In fact, they sort of spiral around the surface, around the heart, coming to its apex. This is called the base. This is the apex. They spiral around, so when the heart muscle contracts, it sort of spirals on itself, kind of wrings the blood out of itself, if you will. All right? Okay, continuing to zoom in on the microanatomy of the heart. Here's a little cartoon of the myocardiocyte, the cardiac muscle cell. And one of the things back in the beginning of the year, semester, when I was talking about skeletal muscle, I talked about how it was striated and polynucleate, and contrasting it with these cardiac muscle cells, which were also striated. However, they were mononucleate. And so I'm reminding you of that. The myocardiocytes are smaller. There is a single nucleus in them. There is, of course, many mitochondria so that they can have energy production. And instead of being many cells that fuse together to make a single skeletal muscle, each of these myocardiocytes are joined to one another via these intercalated discs. These intercalated discs, we see them here in this histology here. All right, and it's the end of one cell joins with another, intercalates. To intercalate with something is like your fingers interleaving with one another. Here, all right. So my two hands are intercalating. An intercalating disc is this sort of cap end on a myocardiocyte where it joins in close apposition to the adjoining myocardiocyte. And they're held together by desmosomes. You'll remember those when I talked about the different cell adhesion molecules. And they are also joined by the gap junctions. Gap junctions, you'll remember, are like the grommets, the little holes, the passageways. So what happened, the upshot of this is because there are these numerous gap junctions connecting adjacent myocardiocytes, they are synstitial. They are synstitial, meaning that the cytoplasm of adjoining cells, they're confluent. All right? And the result of which is that when you have contraction in one myocardiocyte, it's able to spread to adjacent myocardiocytes. So unlike in skeletal muscle where you have one large muscle fiber that's going to be able to contract, you're able to do even larger tracts of tissue in the myocardium because of this synstitial gap junction infrastructure that we have here. Okay? Does that make sense? So cardiac muscle is involuntary. It's involuntary. It's self-stimulating, self-depolarizing tissue. All right. I go over here. I lift up a book because I think about it. I make my muscles contract, the primary motor cortex, all that. This is not how the heart works. Of course, you don't have to think about your heart beating. It does it for you. And it does it by virtue of these Purkinje fibers. These are specially differentiated myocardiocytes that are able to initiate depolarization in the myocardium. Okay? Purkinje fibers are what initiate it. And these Purkinje fibers make up these depolarizing, self-depolarizing cells make up what's called the conduction system. And we have it here drawn in this cartoon. The components of the conduction system, the top of it, this I guess the first domino in the chain of depolarization is what's called the sinoatrial node, and this is a bundle of tissue that's located in the wall of the right atrium near the entry point for the superior vena cava. It's called the sinoatrial node. This is where depolarization starts and then extends from there via these internodal pathways converging upon the AV node, the atrioventricular node. This is another bundle of fibers that is located in the myocardium at the juncture between the atria and the ventricles. So it's this SA node that starts the cardiac cycle starts contraction in the atria, and then it sends its signal down to the AV node, which is going to be responsible for controlling contractions in the ventricles. The AV node depolarizes and will send its signal down this AV bundle, which then arborizes into these bundle branches that will control the right and left ventricle. And then there are various fibers, these terminal arborizations that end in the Purkinje fibers deep within the myocardium, okay, of the wall of the ventricles. So that's the basic anatomy. So this is kind of an overview of the cardiac cycle. I'm going to go through all of this in detail, but I'm giving you this as an overview of what we're going to talk about. So this electrical stimulus that starts at the SA node, is distributed across the conduction system down to the AV node and to the bundle, etc., the bundle branches. This distribution is going to, this electrical activity is what gives rise to the electrocardiogram, the ECG, that we're able to pick up with patches that you stick on the chest that can monitor the electric field that's generated by the heart, by the conduction system. This conduction system is going to be what contracts the heart. It stimulates the contraction. This contraction is what gives rise to the heart sounds, the lub-dub that you hear when you put the stethoscope on the heart. And of course, it pumps the blood. It gives us, maintains our blood pressure and blood flow, etc. Okay, so just to look at what this means in terms of membrane potential, if we were to look at the cells at the SA node, where here we are at threshold, there's going to be a depolarization and resulting contraction, etc. And then we repolarize using the sodium-potassium ATPases. We're going to reestablish the potassium will flood in, and then the sodium-potassium ATPase will reestablish the correct electrochemical gradient. However, the leak channel expression patterns in the myocardial membranes are not the same as skeletal muscles. So they continue to leak, and there's this spontaneous depolarization until the cell reaches threshold once again, and then has a spontaneous depolarization without receiving input. All right, so we can reset the membrane potential, but it's too leaky, and it spontaneously depolarizes to threshold. All right, that's how this works. It's just by controlling the expression patterns of the various channels that are expressed in the membrane of the cells in the conduction system. So yes, Jacob. Hi.
So those are all voltage gated, or what is the gating system on this channel?
The threshold, when you reach threshold, that is absolutely voltage gated. Yeah, absolutely. Okay, so the conduction system here. Step 1, SA node spontaneously depolarizes. Those cells in synchrony reach threshold, and we're going to begin the impulse conduction. So this stimulus is going to spread across the atrial surface through the internodal pathways, converging on the AV node. It takes about 50 milliseconds. By the time it reaches there, both atria are going to begin to contract. All right. So as the atria are contracting, we have now set off. We have triggered depolarization in the AV bundle, which is going to begin to send a signal down the bundle branches. So we are in atrial systole, still meaning contraction. We're still in ventricular diastole, meaning relaxation. The ventricles have not contracted yet, but the stimulus is coming down the bundle branches and the moderator band. Moderator band is a consequence of this unique anatomy in the right ventricle. I don't want to get into that at the moment, but so the stimulus then spreads out through the Purkinje fibers into the myocardium of the ventricles, and those ventricles are going to begin to contract. All right, and as they do, the moderator band helps to pull the AV valves closed, the atrioventricular valves closed, the tricuspid and bicuspid valves closed, and these are going to contract and lead to ejection of blood. Those are the 5 steps. All of that conduction activity gives rise to what we call the ECG. It used to be the EKG, but that was cardio spelled with a K because it was the Germans that first came up with this technique. So here is an ECG trace and expanded. If we look at the ECG trace, it has this characteristic pattern, and the pattern has been given discrete names. So there's the P wave, there's the QRS complex. So here's the P wave The Q is the downward peak, R is the upward peak, and S is the subsequent downward peak. The QRS peak complex, they call this the QRS complex, and then the T wave following that. And each of these three features corresponds to specific conduction pathway events. So the P wave is recording the activation of the atria, so the spreading of the conduction across the internodal pathways. The QRS complex is the activation of the ventricles. So you can begin to appreciate that the ventricles are significantly more muscular. It's a much more intense. It's a much more intense event that's happening down there. And if you think about it, because the atria, they just have to push blood down into the ventricles. They're not ejecting blood to the furthest reaches of the body, right? They just have to like shove all the blood that they've collected down into the ventricles. So these P waves, the P wave is modest. The QRS complex results from the massive depolarization in the ventricles. And then there's this T wave, which is the repolarization of the ventricles. And significant enough to register here. The repolarization of the atria should be very modest. If you compare the relative dimension of the QRS complex and the T wave, the corresponding repolarization of the atria would be a very minimal bump that is not able to be picked up by the ECG if it weren't swamped out by the QRS complex anyways. All right. Okay. So a little bit more about the specifics of the action potential in cardiac muscle. Is this? Am I going at the right pace? Am I flipping too fast here? Is this okay for everyone? Okay. So in skeletal muscle, if you were to look, so here's an action potential in a skeletal muscle, all right, and it's going to lead to a contraction, and this is comparative time scales, right? So this action potential has a refractory period that is comparable to the excitation phase of that action potential. Do you understand what I mean by that? So that the upward slant of that curve is comparable in duration to the refractory period. So the blue is the absolute refractory period. Here's the excitation phase over here, and this is the relative refractory period. Now, if we compare that to cardiac muscle, so the point being that a lot of contraction, the production of tension in a skeletal muscle falls outside of that refractory period. The bulk of the contraction falls outside of that refractory period. This is what enables us to have wave summation, Trappé wave summation, and lead to increasing tension, and eventually tetanus in the muscle, right? Tetany. That can happen because the bulk of the contraction is outside of this refractory period, so we can have subsequent contractions that are continuing to add to that tension in the muscle. In cardiac cells, however, there's this extremely long, so these are the same time scales. Compare the action potential in the skeletal muscle to a cardiac muscle, there's this extremely long absolute refractory period. Extremely long absolute refractory period. There is a comparatively shorter relative refractory period, but this relative refractory period is still significantly longer than it is in skeletal muscle. If we then compare the refractory period to the development of tension and relaxation in the cardiac tissue, the bulk, the vast majority of the contraction tension in cardiac tissue falls within the refractory period. All right? Why? Why is that? Why did we evolve that? Jacob.
Because you want the heart to contract the same amount every time. You don't want that summation in the heart.
Okay, what would the problem be with wave summation in the heart?
Your blood pressure would skyrocket.
Potentially. I'd have to think about that one. That's not the answer I was looking for. What?
Well, if you got the tetanus, then your heart would.
Thank you. Very, very, very good. Yeah, if you got to tetanus in the heart, what are you going to do then? You're going to get eaten by whatever was chasing you, and the genes that allowed this to happen to your heart are not going to be propagated, right? So tetanus in the heart means the heart is unable to contract any longer. It has maximum tension. There is no relaxation. It's not going through the rhythmic, reproducible contraction cycle. You were on the right track. He just took it home. All right. So, oh, yeah, he read the slide. Often I ask questions that the answer is on the slide. All right. So here is an overview of the cardiac cycle. So again, definitions. Systole is contraction. Diastole is relaxation. Systole is contraction. Diastole is relaxation. So we're going to start right here at this point. We are at in ventricular and atrial diastole. They're both relaxed. We have been passively filling the heart with venous return. All right, but we're about to commence atrial systole. The atrium contracts right here, shoves as much blood into the ventricles as it can, and then atrial systole ends. And we have this second. We have at the end of atrial systole, we begin ventricular systole. So the ventricles begin to contract. They reach the point where the pressure of blood in the ventricles equals the pressure of blood in both the pulmonary circulation and the aorta. These valves open up. The pulmonary valve, the pulmonary and aortic semilunar valves open up and eject blood. And that systole happens up to 370 milliseconds. And then we enter ventricular diastole, relaxation. And this is where we get venous return filling the atria for the beginning of another cardiac cycle. So, yes, sir.
Are the volumes of the atrium and ventricles relatively the same?
That's a good question. The atria have these things called the auricles on them. I didn't go through the anatomy of the heart in detail, but for sake of time. But there are these things called the auricle, which are like when you're looking at a heart. Let me just do this. I can pull up a slide that I hid so we can actually talk about something together. Where is it? Oh, I might have deleted them. I guess I did. Yeah, you can kind of see it here. You have these little flaps. You know you're looking at the front of the heart. If the heart looks like kind of a pig to you or a dog or something, it's got these little ears that are flopping down over the front of it. That's why they're called the auricle. You know you're looking at the front. These little flaps are able to fill up during venous return. They expand to accommodate more blood. There's not much muscle in the wall of the auricles, but even though volumetrically it seems like the ventricles are larger, it's because their walls are much more muscly and they can't collapse down the way the atria does. The atria takes up transiently less volume than the ventricles do, but it's because they are more deformable. Does that make sense? Yeah. Where are we? Here. So this slide here is really the crux of the lecture. Yeah. If you can, there's a lot on the slide, but if you can appreciate how this integrates everything, then you'll understand what I'm talking about today. So this is time across here in the x dimension. On the top, this is the ECG. So that is a proxy for the conduction system. I already told you how to interpret the ECG. And so that is going to tell us when we're getting atrial depolarization, ventricular depolarization, and then the repolarization. Okay? Here, this chart looks at pressure. And it looks at pressure for three different things. First of all, the left atrium in blue, the left ventricle in red, and the aorta. We're ignoring the right side of the heart. Okay. And then down here, this is looking at your volume, your ventricular volume. All right. How much blood is in that ventricle? And we'll interpret that in a bit. Because it turns out that looking at ventricular volumes is extremely important when you are interpreting what's called cardiac output, which is essentially how much blood your heart can put out in a minute. All right. So first, the left atrium. There's this passive filling and depolarization during the systole. So the pressure goes up in the left atrium as the atrium is compressing on that blood and shoving it into the ventricle. And we see the ventricle rise in pressure in accordance with that. And then the valves close, the AV valve closes, and we begin ventricular systole. And we're right at the QRS complex right here. And pressure starts to skyrocket. The pressure in the ventricle, when the pressure in the ventricle equals the pressure in the aorta, okay, equals that systolic blood pressure, then the aortic valve snaps open. It's not going to be able to snap open until these pressures are equal or exceeded. Once this happens, then blood flows out into the aorta, and we begin to see the aortic pressure match the ventricular pressure until the aortic valve snaps shut, pressure drops, and we begin refilling. Okay? So let's look at the volumes. We have passive filling here during 1. So this is venous return. We have atrial systole. So we begin to shove blood down into the ventricle. So the pressure goes up. And we get to this point of end diastolic volume. It's the end of ventricular diastole. All right? The ventricle is about to contract. How much blood is in that ventricle? How much blood is there is going to dictate how much blood it can pump out. So the higher your end diastolic volume, the greater your cardiac output. Okay? And so then we have the contraction. And we get down to your end systolic volume. This is how much volume is in the heart, in the ventricle, after this AV valve has closed. Or not AV valve, I'm sorry, the aortic valve. The aortic semilunar valve. This difference between end diastolic and end systolic volume is what we call stroke volume. Stroke volume. For one stroke of the heart, how much blood was ejected? That's the stroke. For each stroke of the heart, what is the volume? We call that stroke volume. That's important. We're going to come back to stroke volume probably actually in the next couple slides here. So I couldn't fit it all on the same slide, but if I could, I would have slid this one in on the bottom. I know my slides get a little bit complex sometimes, but This is just the heart sounds, the stethoscope, the lub-dub, right? That lub is the AV, this is the semilunar valve snapping open. There's these 4 heart sounds. There's the S4, that's the atrial ejection. The big lub, this is the semilunar valve snapping open, and then the dub is the semilunar valves snapping shut. All right? There are all these, so the process of listening to the heart sounds is called auscultation. For your own edification, it's called auscultation. And these are the different places on the chart, on the anterior body wall where you can get various sounds. So, for example, here, this is a good place to listen to the aortic valve. Over here, this is where you're going to listen to the pulmonary valve, etc. There's just a chart telling that I'm not expecting you to know all those sites, but so that you're familiar with the fact that when you listen to different places on the chest wall, you can listen to different functions of the heart. All right, so on to cardiodynamics. I'm probably not going to get to autonomics now that I went on my little field trip down there. But so we talked about, in general, cardiodynamics means the movement and force generated by cardiac contractions. And an analysis of cardiodynamics gives you an insight into the fundamental cardiovascular health of the individual. Okay. We defined end diastolic volume as the amount of blood in the ventricle before it's ready to contract. We defined end systolic volume as the amount of blood remaining in the heart, in the ventricle, after it has contracted, after the ventricle has finished its systole. Right? Stroke volume is the difference between those two. All right? So we denominate that in milliliters per beat. So how many milliliters did it eject per contraction of the heart? All right? And we calculate it by the difference of the two. The ejection fraction is the percent of the end diastolic volume that the stroke volume represents. So this total here, we have this on this diagram, we have this set at 130 milliliters, 130 milliliters in that left ventricle. And at your stroke volume, this is showing 80 milliliters. So in this diagram, the percentage would be 80 over 130. The cardiac output is the volume that the heart is going to be able to pump in a minute. All right? So that we can get a sense of how much blood the heart is able to provide to the rest of the body as a unit per unit of time. And the way we get that, since this is milliliters per beat, we need to multiply milliliters per beat times a number that's going to have units of what? Beats per minute. Right? And what is beats per minute? That is your heart rate. That's your heart rate. So if you multiply your heart rate by your stroke volume, that's going to give you your cardiac output. And cardiac output, the rest of the discussion about cardiodynamics is going to talk about ways we can affect cardiac output. All right? So I want you to understand its definition. We're going to look at how we can affect cardiac output. And clearly, they're going to be either through affecting the heart rate or affecting the stroke volume. And we can affect both of those. And we'll see how that's done next. All right. So on the heart rate side, you can either do it with the nervous system, of course the autonomic nervous system, sympathetic and parasympathetic innervation, or with hormones, various hormones. On the stroke volume side, you can either affect the end diastolic volume or the end systolic volume. So I think I am going to go ahead. I could have ended here, but let's start with the autonomic innervation of the heart. So there's the sympathetic, fight or flight, and the parasympathetic, the rest and digest. Let's start with, you guys want to rest and digest, or do you want to fight and flee first? Fight and flee? Matt wants to fight and flee. All right, so this is going to start, the initiation of sympathetic input is going to start in the cardio-acceleratory center of the medulla. It's going to descend to the ventral or lateral horn, emerge through the ventral root, pass through the white rami communicantes, which you're probably all painfully aware of now. It's going to synapse there, and then emerge from a sympathetic nerve via a postganglionic fiber that is going to contact the heart and have a cardio-acceleratory effect on the heart rate. On the other hand, the parasympathetic nerve is going to be in the cardio-inhibitory center that's just adjacent to the cardio-acceleratory center in the medulla. From there, it's going to project to the vagal nucleus. So when I was talking about the cranial nerves, I didn't talk about many of them, almost any of them in any detail, but I did mention the vagal nerve, the vagus, right? The wanderer of the body, the wanderer. Well, this is how we're getting out of the nervous system, is via the vagus nerve. It projects from the vagal nucleus via the vagal nerve and sends branches down to the cardiac plexus, which are going to have the effect of slowing the heart rate. And we'll talk about how this happens in terms of the receptor structure, whatever, on Friday. All right. So let's see how they achieve it in terms of membrane potentials. Here's your heart rate unaffected. Since we're fleeing and fighting first, we'll look down here. The sympathetic stimulation with norepinephrine is going to lower that threshold. It's going to lower the threshold. So this spontaneous depolarization doesn't have to depolarize as much before we reach threshold and have a stimulation. This is going to have the effect of compressing compressing the contractions of the heart. The heart rate, for example, here was at 75. This takes us up to 120 BPM. On the other end, and so we call an abnormally rapid heart rate tachycardia. Like a tachometer on your car shows you the RPM, how fast your engine's spinning. Tachycardia, the speed of the heart, the unnaturally racy heart. And then on the parasympathetic side, it just has the opposite effect, using acetylcholine. It raises that threshold where the cell has to, no. What it's doing is changing the repolarization. It's not shifting the threshold. That was I was misspeaking there. Please forgive me. It's not changing the threshold. The threshold level is the same. On sympathetic, it's reducing the level of repolarization. Okay? Forgive me. It's basically shifting this curve up a little bit, but the membrane the membrane dynamics are the same. So it's the same threshold. For the parasympathetic, it's shifting it down, so it's hyperpolarizing that cell. It's sending it to a lower membrane potential than it would have been normally. Normally it goes down to -60. Here it goes down to -70. So it has a further course to run before it reaches threshold. Here on the sympathetic side, it's only going down to maybe -50, something like that. So it has more rapid depolarization, less to go before it reaches threshold. A slowed heart rate is called bradycardia. So tachycardia is fast, and bradycardia is slow heart rate. So yeah.
So the vagus nerve is going to be sending the signal to slow it down. Which nerve is speeding it up?
Those are sympathetic nerves. Sympathetic nerves emerging from the sympathetic chain ganglia. All right, so I'm not going to get entirely through this today. I got sidetracked there, but we'll start. So that is how the nervous system is going to affect the heart rate. All right. What about stroke volume? We said that you can affect stroke volume by changing end diastolic volume or end systolic volume. Okay. Well, and we're going to go through each of these up in the top here. The first is venous return. Now, venous return is how much blood is coming back from the periphery. Okay? So if you have an increased venous return, if more blood is filling the atrium, then you're going to have a larger end diastolic volume. This is going to increase the preload. I guess I didn't define those terms. Oh, they're right here. Yeah. Preload. So it's the volumetric pressure that's going to stretch the ventricles either right or left. All right. So this is how much blood are you able to stuff in there. The afterload is the pressure that it's working against. All right. So the lower that aortic pressure that the ventricle is working against, the lower the pressure threshold for the doors to swing open is, and the higher potential for ejection there are, and consequently larger end systolic volume and stroke volume. So if you can increase preload, you're going to increase stroke volume. Decreased venous return leads to decreased end diastolic volume, which is going to decrease the preload. Preload is going to affect both end systolic and end diastolic volume. I'm going to leave it there. We'll finish up with this slide. That was essentially the end of the lecture. I got thrown off a minute or two there by running around. We're going to pick up next time with this, and then I'm going to move into discussing blood pressure, how we regulate blood pressure on Friday, and then quiz on Monday. Are there any questions?